Yeah, sure.
Yes, you see, no matter what the system you are studying, and ultimately you have to deal with the interaction among agent, right?
Yes.
And of course, these agents are physical, but the idea in standard models we can in physics is the reason I'm critical about this standard model because they are not dealing with the physical particle. They are unable to deal with the physical particle because that idea of the quarks and this subatomic stuff cannot be described by ordinary particle or wave. Very abstract stuff. Okay, the agent you still can talk about individual bird, individual ant, right? Individual buyer, and that is a tangible, right? That is describable. You can.
Yes.
But the idea we discussed last week is it's useful. Because you can imagine that if you are surrounded by people who have the same idea, same experience, same appearance, same character,
completely homogeneous,
or completely, you feel you are isolated. You are in the mountain. You live alone.
Yeah.
That is idea of this the force due to a broken symmetry. Can you see? Does that make sense? If everybody says the climate change has become consensus, so you have no idea, no response to this topic anymore because everything's settled, unless some people like me yell back, and then you say, oh, you get some, you feel some force. Do you agree?
Yep.
Otherwise, if everybody behaves the same, think the same, you wouldn't appear there's a
force.
The force.
So perfect symmetry in all directions.
Yes, probably. Actually, I this morning I just share you the picture. One, not this one. Yes, share screen. Yeah, we can continue to discuss, but before we go, can you say this is a talk I'm preparing. So can you see this picture? I pick up this one particular one. I didn't follow the research in the superconductor, but I was surprised to see that the transition temperature from normal conductor to superconductor can reach 250 Kelvin.
And that's the critical point.
Critical point where they switch to the no resistance mode. And I'm surprised because in the 80s, when the so-called high temperature, high transition temperature superconductor was found, it was around 100 Kelvin. Now this is very close to room temperature now, because our room temperature, is 273. That's or roughly 300. So we have about 50 Kelvin away from the drain. But interesting in our discussion that you can see this structure. Can you see this structure?
Yep.
This notation is called is a lanthanum. Lanthanum is just a special series of elements, heavy element. And lanthanum element surrounded by H for hydrogen. Can you see this tiny ball are all hydrogens?
Yep.
Now, as a result, this particular element, lanthanum element, was surrounded by a symmetrical hydrogen cage.
Yep.
That makes sense. So that is one reason that you can see that. Of course, there's no direct connection, but certainly you can appreciate that the high degree symmetry can somehow to reduce the electrical resistance.
Right, and does the symmetry breaks at the critical point? Is that? No,
they form symmetry at critical point.
Okay.
You see, it's the other way around, because you see, you have gradually appreciate this idea that the relation between force or interaction and the symmetry of the symmetry of your environment.
Yep.
So the more symmetric and zero, the force interaction getting zero. That is the idea.
I was reading a really interesting. I'd be interested to see what you think. So one of my professors, is doing research on a topic which he calls guided self-organization. This idea of self-organization.
Self-organization is from far from equilibrium state, right? And
Right.
something might change or self-organized way.
Yeah.
Self-organized way.
And he was talking.
Okay.
I was reading one of his papers, and he was talking about this idea that between complete order and then a completely chaotic system, you have this idea of a complex system.
Can I grab some cup of water?
Yeah, of course.
Yeah,
sure.
Okay. Yes.
Symmetry and force. That's what we were discussing. Yes.
Yes, that's right. Symmetry and force. And so what did you?
Oh, yeah. So I'm trying to figure out if I can explain it properly. Basically, in a nutshell, it was this idea of organization, self-organization being more order, right? So the system becomes
they generate order. They can locally generate order. Yes, that is the idea.
Yes,
it's just like any biosystem, like a human.
Yes.
Before we die, we're always trying to overcome that disorder.
Yes.
You see, we're trying to organize to make everything in order. You see, communication, nervous system, visual, and hearing. So this is a kind of ordered system, highly ordered system. Yes.
Yes. But but not like I see. Not like a gas in that way, not like a traditional thermodynamic system.
Gas is very simple system. Gas, relative speaking, among because gas has you see can easily describe by the identical particles.
Yes.
Now so when we talk about chaos, probably gas is not good unless except we're talking about the vortex, when the flow, right? You can imagine when the gas is flow in the air at different pressure or temperature gradients, and they will be in a very disordered situation. Unless, of course, they can also, as you say, emerge in a self-organized state somehow locally.
Locally. Okay. Interesting. Anyway,
but you see, the important thing is to understand the mechanism, how the system can, to some degree, at a certain time, to organize, to counteract the second law of thermodynamics. That is something amazing. Whether that is simply due to the complexity or number of the elements or agent, I don't think so. But people are, you see, so my understanding, you can later inform me as well, any other approach. To my knowledge is that the self-organization is a kind of, people are in favor of the trust some simplified differential equations. They think that there's some magical moment where the phase diagram will appear and very regular.
Yeah,
they're trying to, they're trying to ignore the fundamental action or interaction.
Yeah, absolutely. I think what do you say? The ab initio approach, not so much. I think it's a lot. The ones that I've come across are very much focused on, as you say, qualitative changes in the phase space. And have you heard of Hermann Haken?
Hermann Haken, kind of, not very familiar with name. No.
He's a German guy, but I think he was sort of the guy who came up with synergetics.
It's kind of it's kind of it was very close to self-organization, right? It generate something new phenomena, right? Emerging something. Is from the chaos, right? Order from the chaos. Is that similar to that
a similar concept.
Order in chaos. That is people trying to draw people's attention.
Yeah, I don't.
What is the point to mention this particular guy?
Well, so I remember I was asking you, I was like, oh, what's an order parameter, right? And I traced sort of
probability is order parameter.
Oh, really? Okay.
Probability, yeah. They focus the more the individual microstates, that's from thermodynamic point of view, the more the different microscopic state, the more chaotic the system is, or the larger the entropy is.
Okay. Well, he's maybe he's bastardized it, but my understanding is that his approach to these complex systems is you have huge numbers of variables, but his idea is you can reduce the dimensionality and focus on a handful of so-called order parameters, which are the things which control these qualitative shifts in the phase space.
Yes, so, sounds interesting. Yeah.
Anyway, I don't quite understand it, but I thought I'd mention it.
Well, I think it's certainly just like it's simple, because we're not trying to apply any particular theory. We're just trying to work out the idea.
Yep.
I think my first response would be just simply like the you solve the coupled linear equation. You say for example, you have 3 or even more. For example, we have the 30 or even 100 coupled equation.
Yep.
Among this question, if you do some matrix, if you work out their coefficient in the form of matrices, do you agree?
Yep.
So they probably will go to that.
Yes, like the transition matrix.
Not the transition, not yet. You solve this. Probably we will take this example of the linear equation. So you have the coefficient matrices, right? You got the vectors, and then you became some other vectors. So this matrix is square. You see, that's A11. A12, do you remember the notation? It's A1n, and that is A21 until AN1, and that is ANN. So this is n multiply n matrices.
Yep.
Okay? And of course, this is a general notation of simultaneous equation. So this also can be considered as a simultaneous linear equation. That is the idea we discussed in a linear algebra. Right? Yes, you can by use the so-called matrix. How to say? They can change the dimension. Okay.
Okay.
They can do some analysis. Eventually, they can call the reduction of the row. They can eventually get smaller. So for example, n minus k multiply n minus k. So they can reduce that into the smaller, lower dimensional matrices, and which has the same rule. So what they did is just mathematically to do some selection. For example, they found this in a particular simultaneous linear equation, and this particular row or particular column is not independent, right?
Yep.
So therefore, they can remove it. I think that probably is more concrete example.
Yes.
To illustrate how they can change the dimension of the system. Do you agree?
Yeah, and is that by changing you change basis?
So the number of bases, yes. You change the number of bases. For example, in this in this case, the basis is n, right?
Yep.
So for example, you just probably just use a special case. For example, if you have originally have three bases, right? Three bases, and that is I just use a notation for these vectors. So this is you originally have a 3 notation, and somehow you can reduce to 2 dimension.
I see.
I think that is just example that how the dimension, number of dimension can be reduced. And mathematically, they can argue that by looking at this coefficient, and also they do some manipulation, use a Gaussian or reduction, the Gauss reduction elimination. So they can actually simplify the matrix. So in this way, that will allow you dealing with a problem from 3D to 2D.
And is this purely a mathematical thing, or is this something they're doing with experimental data?
No, that is based on particular system. You can see whenever we discuss things, we just general. This is a very general notation of the system.
Yes. And
each system may or may not have these particular features.
Yes.
Okay. So I think the general idea of that guy is that when you set up a system with n dimension, right? They say, well, before you go further, why don't we consider that whether we can use a smaller dimension to describe the same system?
Yep.
Just because this each system have his own features. That is kind of the strategy people can use.
To simplify.
But whether all system can be reduced to a lower dimension is not necessarily true. This is just a purely case dependent.
Right.
Yeah.
Okay.
Yeah. Well, why not? If you can describe a two-dimensional motion, for example, the good example in physics is this. Can you see? If you let's just take some concrete example. So if you have, for example, in a 3D space, right?
Yep.
You can study trajectory motion. For example, the missiles. Okay, the missiles, the Russian missiles. So in 3D, we say you can launch the missile. So it launches 3D. So the missile will fly. Can you see? Up to the target.
Yep.
You can assume that the missile will launch it like this. All right. So it looks like this 3D motion, isn't it? Because if you look at any position of this missile, these were determined by 3 coordinate, right?
Yep.
And so call its position is P, Y, Z. Can you see?
Yep.
So this trajectory motion certainly is a 3D motion. Okay. So that is Y, this is Z. Look like a 3D motion. Can you see? It's a target. Now, however, if you deliberately choose you say, can we just choose a spatial plane? You see, that is something that's probably easier for you to understand. If you choose a particular plane, so that the trajectory were on this particular plane, can you see?
Yep.
This plane is 2D. Do you agree?
Yes.
So in this way, this 3D motion can be alternatively described by what can we use a Y dash? It's different to Y, so it's a Y coordinate. This is X dash. Can you see? Can you see that is a perfect illustrate this called dimension reduction issues. So in these new studies, we are not obliged to use 3D, but use just 2D. Can you see? Same position, but by just use two variable. I hope this example will help you to understand why sometimes we can focus on lower dimension.
That does help. Yep.
Yeah.
Absolutely.
This is right name for this is called the project. This is a typical. So this actually will be used to design the missile. This is called project motion. So this is a project motion, projectile motion. So you see, sometimes we can use some concrete example to illustrate the abstract idea. But how far you can go is case dependent, right?
Right. Yeah. And this requires you to have a pretty good knowledge of the system.
knowledge. And also, but for mathematicians, they don't have to refer physics. They're much smarter, because you see, mathematics is such is a very accurate or it's very precise logical analysis. So, for example, when they probably would not have to consider this particular, the movement of this project motion. They probably, if we write this formula give the data in the form of these matrices, they could smart enough to use their what they call a different theorem in mathematics to work out the same conclusion that in this case the dimension just can be reduced to 2. Okay.
Right. Very general.
But yeah, they can use a general approach to this case. Well, of course, they have to do so. You must provide concrete matrices for them. Okay. So you say same goal but different road. Every road go to Rome. That's probably the idea of these guys' ideas. Yeah.
Well, I suppose getting the matrix is the difficult part, right?
Well, that is what you can do. You see, you imagine that if the guy have no idea, for example, they set up the observation, they put a telescope or radar system, and they just repeatedly record this the position in their coordinate. All right, and they can eventually generate the matrices. Can you see? They can generate matrices as a function of time, the T1, and another matrix, the T2. Okay. And that becomes some called the data science. You see, you got a lot of data.
Yes.
And before you're dealing with data, in order to find, of course, ultimately they're trying to solve eventually they need to find this trajectory. Can you see? Finding the trajectory is another issue, very important issue in physics. Okay. And perhaps we can take this opportunity to discuss this issue. How do we know this is the most probable trajectory? Why does the method go this way, or the method does go this way to reach that? Why do the method have to follow this particular trajectory? That is a fundamental issue in
least action, right?
Least action, yes, you know that least action. That's a very important idea. So obviously that is it's called the least action, the principle. Yeah.
Hamilton, right?
Yeah, Hamilton principle. No, this action is due to Lagrange.
Oh.
I said notice at Lagrange, but people say Lagrange. Lagrange principle. Principle. Least principle of least action. Yes, we can discuss something like that.
Okay, well, I've heard it referred to. It's a variational.
Yeah, this action. So this action is either physical or mathematical. You will notice that. So the idea is that actually the action is denoted as S, and then this called action. Action is equal to this probably general notation. They got L and dt from T1 to T2. So you can imagine this event happen between T1, the launch, you push the button, and until the landing occur. See,
and all the dynamics are just summed up in that Lagrangian L.
So basically, they argue that these actions somehow you have to find you can choose any parameter, say lambda, right?
Yep.
To describe this action, and during this among all these path integral, you can see the path integral. Gracie, did you mention that before?
Yes, Feynman. You mentioned it briefly. Yes.
Integral. This part. Yeah. Actually, Feynman uses this action as well. Oh, so did Einstein.
I see.
All of them, they use this principle of least action. Actually, yeah. So what is it argues that if you say this is least, this is for example, if you use a purple color, somehow you have, if you put all this together, so lambda is just departure from this the most probable or least. Can you see? So now there exists in the particular value at which at this particular value, then that is the most probable value.
Yeah. Okay.
So therefore, this value is governed which trajectory you end up with. Yeah, so that is very important ideas, similar to the symmetry, the broken symmetry and action. So if you wish, we can probably discuss this as well.
Yeah.
And you see that is the path integral. Oh, that is Lagrange. So this L here. So what is L? And can you see that L here? So L is Lagrange. Yeah, these guys appear many times in Lagrangian. Use this adjective form, Lagrange.
And there's always optimization with Lagrange, I've noticed.
Well, Lagrange was, or Lagrange mechanism was developed from Newton's mechanics. Hamiltonian is different, slightly different approach. Hamiltonian is different. So this is not Hamiltonian. Did we mention these two guys before?
Yes, we have. Yeah, the idea of Lagrange came first, and then Hamilton worked on Lagrange.
Yeah, so basically this idea is the original. This is developed the idea from energy formula. You see.
Yes.
So basically that use the EK take E potential, and the Hamiltonian just use the total energy, the plus. Yeah. Yes, we mentioned that before. So that is so the first in Lagrange, and none is a Hamiltonian.
Yep.
Hamiltonian. And they're both a mathematician, but they are very, very clever because they saw the alternative, they found alternative to dealing with the issues, the basic issue in physics. And so nowadays we, of course, in the Newton's, in particular, so in the Newton's law, so in Newton's mechanics, the EK is can be only written in this form. That is can use velocity. And EP can also written in this form. That is potential energy. So that is or we just use perhaps use U, which is a function of the space variable. So it's just notation. So important things, the starting point is from this is Newtonian mechanics. Newtonian mechanics. Of course, the reason that's why they have confined, they have, no matter what they do, they have to refer to this particular kinetic form. The potential form is such, they have the very, they also implied another condition people didn't realize, that the force, the ordinary, we talk, see, we return to the force again, because in the Newtonian mechanics, basically we are dealing with the force. Okay?
Yep.
So in Newtonian physics, we are dealing with force, which is, according to Newton, is equal to ma, right? Ma just the dv dt. There are many ways to write the dv dt, or if you wish, you can just write as n x dot dot, the second derivative.
Yep.
Okay. So in both Hamiltonian and Lagrange mechanics, they have assumption that they can get rid of, we can represent the force. So basically they have assumption that the force discussed in Newton's mechanics can be simply written as the first derivative of the potential energy. And which is true so this is true for both gravity. So this formula is valid for both in several occasions, they are valid for several cases. So including the gravity. So this force, for example, the first, so this basic force, so this is a force. So this is a force in physics. So which satisfies this condition includes the gravity.
Yep.
And the electrostatic. So there's a Coulomb's law, electrostatic force. According to Newton's law, the gravity is a force can be written as G multiplies R squared and M times M. This is Newton's gravitational law. Coulomb's law, I used to say here, can be simply written as K multiplied the two charge. So that is a fundamental. These are two fundamental interactions outside nuclear.
Yep.
And inside nuclear, we have introduced other interactions, which may the formula which remains unknown. So you can imagine that in both these cases, the force can be written as this form.
Yep.
So if we just assuming that the potential energy in this case can be written as a negative, a constant. Can we say just because this after all is a constant, right? Can we just use a common constant? Can we use just alpha, right? It's constant divided by r. So if you do this, then in that case we can use R notation. That if we just assume the potential energy can be written as R, or you can use X if just for one dimension, right? Okay, just can be written as negative alpha X squared. You see, just X.
Yep.
So in both cases, so in this case, alpha is either equal to GM, or alpha also can represent the KQQ, right? So you have, so this, what I mean is that in both cases, we can use this formula for potential energy.
I'm just trying to think what that graph looks like. Is that just a
decaying? You can draw the graph. Yes. So basically, this is a basic idea about the three different mechanics. So of course there are other forces. I just can write one more, which is not this is not the third one is not fundamental. It's called the elastic force. Elastic force.
What is elastic force?
Like spring.
Oh, okay.
Our spring. You know, this is a typical elastic force. Can you see? Actually, the spring can be described as a constant of K. Spring. In this case, the force is follows the Hooke's law, which is Kx, right? But in this case, in this particular case, the potential energy can be written as a half Kx squared. I think this is a good example. Can you prove the Hooke? Can you prove elastic force? So this is a force. So this is you can see there's is upward, right? This is the force up. This is a force satisfies this condition. Can you prove that? We can do some mathematical integration. Calculus exercise.
Yes. So we're looking for the derivative of f of h. We're looking for
derivative of the potential energy. So this is a potential energy. Can you see?
Okay. Yes.
This is a potential energy.
Right. So we've got our generic formula. Is a negative constant. Oh, so it's just negative alpha over x.
No. We are focused on this one. We'll just prove this elastic case now.
Okay.
Probably we don't use this. We have too many formula. Can we just focus on this formula? Can we just focus on this formula? So this is our first formula, right? This is our the first formula. This is our second formula. Can we just go for third formula?
Du dx equals 2. We move the 2 half times half k x to the negative. Actually, no, just k to the x.
K to X, K to X, yeah.
Yeah.
Can we simplify a little bit?
Yes, equals kx.
Yes, what is Kx?
Kx is.
You forget you have put a negative sign here. Can you see there's a negative sign here? We have put the negative.
Oh yeah, sorry, negative.
Yeah.
So
what is negative Kx? You're looking for another condition. So this is Kf. So what is it? Negative Kx?
Oh, that's our elastic force.
Elastic force.
Yeah.
That makes sense.
Yes, it does.
So indeed, so in these three cases, okay, in these three cases or these three type of forces, the Lagrange and Hamiltonian's idea is valid. So we don't have. So basically, we don't have talk about the force explicitly,
right,
in Lagrangian and Hamiltonian mechanics. Does that make sense now?
Yeah.
Because we have smartly, we have mathematically to represent the force as the first derivative, negative first derivative of the potential energy. You can see that is how mathematics can do, given that basic natural law, and they can rewrite the form. They can find a different form.
Yeah.
So basically, that is so from here you can see that both in Lagrange and Hamiltonian mechanics, we're still talking about the force, but in the disguised form, okay, in the hidden form. The force became invisible in the formula.
I see. It's all energy.
And that is right. So,
okay.
that is something very important before we go further. So they return to Lagrange mechanics, which is directly associated with the definition of action. So if you just discuss Lagrange first.
Yep.
If you talk about Lagrange's mechanics, so we know that the L, you see, the L is equal to the half m. This time I just use the x dot as velocity. Just change the notation slightly. Can you see?
Oh, yep.
And the minus that is the potential energy, which is can we just consider the spring, okay, elastic spring. So we have more concrete form, right? Okay. So that is for a spring. So mass on a spring.
Yep.
So this is Lagrange for this particular simple system.
Yep.
Actually, don't underestimate this exercise, because this is a foundation for people who build like Richard Feynman and others to build the quantum field theory.
Right. Okay.
Yeah. Of course, to actually borrow this idea, they have overcome many odds. For example, how to define the kinetic energy of field with no mass, no charge.
Yeah. Right.
Yes. So that is probably something we can go further. But today probably we just go through this the least acting principle. All right. So basically, by definition, so S were equal to this T1, T2, right?
Yeah. Yep.
And that's L dt.
Yep.
To be precise, we can put some the variable here. That's x dot, which is velocity, and the time.
Yep.
So that is action. By definition, this is action.
Yep.
Okay. Now to get the minimum dx, so we have to introduce something in order to get can we just introduce something which is slightly different from this just like differentiation.
Yep.
Maybe I don't want to use the notation. I use this differentiation. Okay. If you just consider the variation of this s, obviously this integral, this path integral will give you different s value. So if you follow the different paths, so this can we just introduce the path parameter? Can we call it the lambda, right?
Yep.
So for different paths, so this is a path parameter. So this is a path parameter, which is just used to parameter, which is just used to represent a different paths you choose, right? So from this is actually what happened. So we got this is initial, they get is the final, right? So this could be lambda 1, right?
Yep.
This could be lambda 2.
Yep.
And so on. So they have different lambda. This is lambda n.
Yep.
So that is how in this case, in this way, you would be in principle get something like this, right? You should get something like that, right?
How are they ordered?
You will compare. Maybe this we introduce this the subscript after we calculate each path.
I see.
You understand? There's no guarantee. If you just arbitrarily choose orders, then that will give you that dependent parabola. Yep. There's no guarantee. Maybe this is a good question. Maybe they just order them after they actually work out each path. So that will be up S1, then S1, or the S2, right? S2, S1, and Sn. Okay, all of them.
Yep.
So basically, we can just do the first derivative in order to get this. Based how to say the least. Of course, we hope that in order to find the shortest, the least action. Of course, we know the straight line, right?
Yes.
Even whatever geometry base you use, Euclidean or non-Euclidean, this is a straight line.
Yep.
You see, that is why Albert Einstein was clever. He trying to get right after he proposed the special relativity. He's trying to explain everything other than inertial, the constant relativity, constant frame relativity. He was not satisfied. He's not satisfied to that special case. So that's why it occurred to Einstein, if he's used his idea of the 4 coordinates, it's called space-time. Before him, that the people consider space and time are separate. So our space still still is. Our real space is 3-dimensional.
Yeah.
But Einstein was the first to, not necessarily first, actually his teacher Minkowski also provide this 4-dimensional space idea, or 4-dimensional. So basically Einstein thinks that, so if we just, they can use what we call the, it is a notation they use. So if we just put the time as additional x, y, z, can you see?
Yep.
Look, this is go opposite. They just go from 3-dimension to 4-dimension. Can you see?
Oh, right, yes.
So it's sometimes you don't have always reduction. Sometimes if you go backward, that will give you more insight. That is why Einstein was very successful in advocate this called the 4D, so 4-dimensional, 4-dimensional vector position. So he's thinking, well, why don't we apply this least action phenomena in the 3D form? Sorry, 4D form. Can you see that? So this that if there's no gravity, and they will come with the same idea of the what we obtained. So we got a straight line. So this is no gravity. Can you see the object removed from here to here?
Yep.
Right. Even Einstein argues that in the presence of the gravity, the mass, a huge mass, right? So the space become curved. Can you see that illustration? Yes. So there is a hole. You can see that there is is no longer flat. So these just come to the idea. So he said, well, we still can argue that in this case, you have 2 positions here. It is a position 1, position 2. You have 2 positions over here, right? The person here. And in the 3D space, we can still find the least action, and which is straight line. Can you see? Which is straight line.
Yes, yes. And is S, see this action term S, is that a scalar quantity?
Yes, it is scalar.
Okay.
It's had a dimension of energy multiplied time. So this in terms of the, so that's no change. So the dimension of S action is equal to joule. Is energy multiplied the time.
Okay.
So in other words, that you would joule and the second. Yes.
Okay.
So that is this joule, this energy, this unit for energy. This is a unit of energy.
Right.
We use the joule.
Gotcha.
So if you continue our story, if we have time, we can do some. Otherwise, we start next time. So basically, in order, according to calculus, according to Newton's calculus, and in order to find this standing point, okay, they call the stationary point. So at here, yes, S dash must be equal to 0. Yes, that's right. So if you to calculate that one, so we have first to rewrite, because in this case, lambda is only a function of L. So these first derivative were equivalent to the dl d lambda. Do you agree?
Yep.
So that is how to apply this, how to find the first derivative for this in this particular case, right? Yep. And here we have probably used some of the some new idea. We haven't studied. We studied a single variable calculus. Okay. Yep. So here we have to use some multi L, right?
Yeah, multivariable. Yep.
Multivariable.
Yep.
Multivariable calculus idea. So how do we do that? So given this function, so this L is have 3 variable, right? X dot, and T.
Yep.
So the total differentiation must be equal to the sum of these 3. We assume that is the parameter path dependent. Do you agree? So we got this just partial derivative, and to lambda to x. Sorry, first to x. Do you remember the chain rule? This looks like chain rule.
Yes, I kind of do.
Yes, then that we're doing this. This is similar to this is the beginning of relativity. It's okay, it's fine. Doesn't matter. This is not terrible. So then that the lambda L with respect to the a second variable. So 3 variable. Okay, we got a 3 variable.
Yes. Okay.
So these 3 variable are x, which is a function of time, right? And the x star, which is velocity, and the time itself. See, so this is a position.
Is this a plus here?
Which one? We haven't finished yet.
Okay.
No, the product. The product.
Oh, that is a product. Okay.
Yeah, this is a product. Yeah.
Okay.
And let's specify this is a time.
Yep.
This is a velocity. Of course, it's better to with some concrete, tangible stuff to talk about. And for mathematicians, this is just step 1. Eventually, they will get rid of this concrete example. They go to more purely go to function and geometry. They actually eventually go to geometry. So after all, if you're interested to know, so the Einstein's relativity is purely the geometry, okay, not the physics. Geometry. So he just uses geometry to interpret the basic law in physics. So both the language and also the expressions that you introduced is purely based on, it's called Riemann, non-Euclidean geometry. Have you heard of non-Euclidean?
Yeah.
So the difference is in the Euclideans, right? You will see the straight line, the parallel straight line never intersect, right?
Right, always orthogonal.
Yeah, orthogonal, parallel, right? Never. That is criteria.
Oh, right.
That is criteria for whether the geometry is Euclidean, Euclidean or the non-Euclidean.
Right, but even if it's non-Euclidean, the basis.
Well, for non-Euclidean, the parallel line can intersect.
Okay.
Intersect. We're talking about that. So basically, yeah, we can talk now if you wish. So if you just imagine this is a hemisphere of the Earth, right?
Yep.
This equator is the equator. So this got a different latitude, right?
Yeah.
Latitude. So for the person at the equator, so these two lines, they can only see locally. These two lines are perfect parallel. Do you agree?
Yep.
Can you see for the person is up two parallel, right?
Locally, yes.
Locally, what would happen if you just follow this direction, go to the North Pole?
Yeah, they converge.
Yeah, they become point.
Yeah.
You see, so that is a typical point that you cannot describe the surface of a sphere as a flat. It's curved. Of course, it's curved. No doubt about that. Yes. The Earth is a sphere. So therefore, they argue that that is why if I say, for example, when I fly from China to America, and they from the map you should go this way, okay? Just go to the parallel to the towards the east, you will arrive the America. But actually, the actual place goes that way to go to north, to go to near Russia, Japan, and to Alaska. Go this way.
Right. Why is that?
Because that is shortest.
Oh, that is least.
That is shortest. Yeah. Yes, that's right. That's probably give you some exercise for you. Right. Before we talk about this Lagrange's least action, can you see? And today probably we just write the expression for you first. So this continue. This is essence. So when you do multiple calculus, you have to look after each variable. Because this is based on the fact, I can finish this first.
Yep.
All of these three variables are also dependent on this parameter lambda. Can you see? If I highlight this lambda here, I'll probably use this red color. So can you see? Can you see this lambda is affected? Can you see?
Yeah.
So, but you have to be patient because this is called a complex function. Can you see? So you couldn't see this parameter. Can you? Can you see the lambda in this expression?
No.
It is implied. Can you see?
I see.
It's implied by choosing different paths, and x dot will become dependent of this lambda.
Okay.
Okay, that makes sense. So this general formula is for the how to obtain the first derivative, if you like. So that is slightly different from the single variable calculus.
And we don't need to include time?
Yes, good question. Do we have to? I don't think so. Because time is, that's good reason not to include that. I forgot. but
I'll take your word for it.
Yeah, doesn't matter. Because I think there's good reason, simple reason. We don't have to consider the time derivative with respect to lambda.
Okay.
Oh, it's good. Well, probably a category we say that the time is different, right? Time will be also depend on lambda, isn't it? Longer time, short time. But they're not. That's a good question. They are not concerned about how much time taken. They merely consider how much action spent. Okay. I would call it effort. Doesn't matter. Some traditional people call it action, but I think it's effort. This action or this effort, whatever. So they don't care how much time you spend.
It's about efficiency. Fundamentally.
Yeah. Efficiency. Yeah, efficiency. Yeah. I don't know. It's not directly. You see, Lagrange is not energy. So that is a question, philosophical question. So you see, Lagrange is not the function itself, the energy itself. Can you see?
Yeah.
The Lagrange is a difference between the kinetic energy and the potential energy. If you talk about, if you consider this is somehow with the efficiency, then you have to mention that the least energy, right? Or there's something we can discuss further. Alternatively, you can see that part of the energy can be utilized.
Right.
Have you heard of the free energy? Gibbs free energy?
I have, yeah.
That is in the context of the thermodynamics. So that's probably just discuss something general. So this Gibbs free energy. Sounds good, free energy. But it's not free. It just means it's available. The energy, part of energy that can be utilized.
Right.
Yeah.
And that's not, that's different to kinetic minus potential.
No, that is that internal energy take away of the, so that is a entropy. You can so say free energy. You can use F. Yeah. I think they use F. I use G or something. Doesn't matter if you use a free energy. That's equal to the entropy, which is H. Take away our product of T multiply S. Now S here is not action. S is entropy.
Okay.
In thermodynamics.
And sorry, what's H then?
H is the entropy.
Oh, okay, right.
Entropy. Entropy is a kind of heat.
Yep. And T is temperature.
Yeah, T is temperature. Yeah. T is temperature is an absolute temperature. It's a free energy. So this gives energy. Well, maybe this is also interesting. We can discuss this issue at a certain stage, because that will answer your question that why there are some, sometimes we can somehow to have the self-organized the emergence of order. Gibbs function will represent how order or disorder the system, how much energy can be utilized to do work.
And is something more ordered has more energy available to do work?
Oh yes, I think so, because mechanical work is in the higher ordered form. See, so you see the car is moving. That's very ordered. Every molecule go one direction. Okay, that's pretty. You can imagine why we cannot use all the so-called energy, available, because if the molecule go different direction, we cannot catch them.
Right.
And that's why we need, for example, when we generate electricity, we have to make sure that every the magnetic field rotated in one direction.
Yes.
So that the electricity can be current can be generated.
Would you if I'm interested to learn more about it during the week, would you have anything you'd recommend? Should I just read the Wikipedia on Gibbs free energy?
Well, we're not going to. Well, I think this we haven't finished this part yet. We're talking about this issue. If you have time, trying to work out what eventually will got what we call the Orner. You can Google that.
Yep.
You will call the Orner Lagrange formula. How did they obtain that?
Okay.
Equation. That if you have time, please just to see how can we from here, we know it must be equal to 0 in order to get the what called Euler.
Yep, and that's the general form. That's what it's called, the Euler-Lagrange.
Well, that is the basic form, and the mathematician also used.
Yep.
Particularly, in the field theory in physics.
Yeah.
They all make this argument that Euler-Lagrange equation is valid.
Yeah. Okay. So this least action thing is very, very fundamental to a lot of physics.
Many people use this. Actually, you can see it's it provides a fundamental approach to the abstract idea in relativity, general relativity, as well as field theory about subatomic particles.
Okay.
Interaction in particular. So not the field theory was introduced to interpret the force. Like say, we will return to the force originally, see? In Newton's mechanics, force is apparent. Okay, they just count the number of force and find the direction of force. Everything can be solved, became differential equations problem.
Yes.
But in quantum field theory, they will reconsider this force. They're trying to use the what is it called action, least action idea to describe the invisible force, invisible field.
Yeah.
I think eventually, I hope this idea will give you some insight to dealing with complex system.
Definitely, I think it's something.
So when we're dealing with complex, you don't have focus on particular entity or elements or agent. Somehow you have to transform this entity or particle, at least their interaction, in different domain into the realm.
Yeah.
That is idea is included in this in the Lagrange mechanics. Actually, they're called Lagrange density. We're talking about that. Okay. Lagrange density is a key.
Okay. Well, I'll check out the Euler-Lagrange equation.
Yeah. What is the Euler equation has anything to not something to do analytically for the least action condition.
Okay. Sounds good. I look forward to discussing it more.
All right. Keep talking these issues. Okay. Goodbye.
Thank you very much. Have a good one. Bye.
You too.